Morning. Well, chips and quantum computing and models might be easy stuff, but PowerPoint is not. And Dawn's experience has me a little nervous because I've been there. One time I built a PowerPoint presentation when I had to present to 4,000 salespeople, and I did the whole thing in template mode, which is apparently a feature, and that didn't allow it to be used at all, so I had to do the whole thing with the app up, and so I feel for Dawn, and I hope it doesn't happen to me. With that, I'm Peter. I'm delighted to be here on day one of the Agentic AI conference here at Berkeley. Thank you all for getting up early to be with us this morning, and looking forward to an exciting weekend. Day one's got a special meaning to me, being at Amazon for 28 years. We talk a lot about day one, and this made a lot of sense when I joined 28 years ago. We were a small little retail startup, and we all fit in a conference room. But you know, as we kept talking about it being day one, it started feeling a little silly as we became a huge retailer. But every day we talked about it being day one, and it meant something to us. And then we started AWS 20 years ago, and it did indeed feel like day one again, because everybody inside the company was kind of laughing at this AWS cloud thing inside of Amazon. But we were very convicted, and that turned out pretty well. And we kept growing AWS, and we kept talking about it being day one. It's always day one. And why do we talk about it always being day one? Because day one culture is something that you believe and will into existence. It's a culture, it's a behavior, it's an attitude, and it's an important attitude. It's an understanding that despite whatever innovations and success you've had, there's more success ahead. And I think it's an interesting way to think about AI, because I think there's a potential to think that we're like on the cusp of being done with AI, but that's not the way I see it. I see this as the very early days of innovation. And what's happening today, while it seems frenetic and exciting and things are literally changing and becoming more capable every day, we're just at the very, very beginning. In fact, I'm an AI optimist. Like, I very much believe, I'm on the far side of the distribution, thinking that AI is really going to help us solve some of the most fundamental problems that humanity faces. Things like energy and health and medicine, and it has so much potential to transform the way we live, and I think we're just seeing the very tip of that iceberg. But in order to get to that future, we fundamentally have to solve a number of problems. In fact, we have to deliver order of magnitude improvement in what's there today. And that's why I say we're very much in day one of this journey. And so really the most fundamentally important problem that I see is that in order to realize what we all want AI to be, we need to figure out how to make AI much, much more efficient. And that is a fundamentally interesting and exciting problem to me, and I suspect to many people in this room. And it's a problem that stretches so many of the pieces of the stack that we're innovating on. And when I was asked to speak this morning, I kind of had this like, what should I talk about? We want to talk about agentic AI, but what is agentic AI? Well, agentic AI is a ton of things, and I am blessed to work at Amazon, where we're working on many of the pieces, in fact, all of the pieces of the AI stack, everything from the applications on the top to the platforms and software and agentic frameworks that allow us to build and secure agents and models, to the models themselves, to the infrastructure and chips that power the AI models and agents that run. But when I thought about what I wanted to talk about this morning, and if I look across the next couple days, there's people talking about each and every part of this stack and each and every part of this puzzle and all the innovation happening. But what do I want to talk about? Well, I thought maybe I would start by talking about what I'm most passionate about, which is the infrastructure. And the reason I'm most passionate about the infrastructure is because, again, I fundamentally believe that in order for us to achieve this vision that I think all of us share for what AI can be, we're going to have to make the infrastructure fundamentally more efficient and not just incrementally. And so Amazon is making some of the deepest investments in innovating at every level of the AI infrastructure stack, and I thought I might start this morning off sharing with you a few of the ways that we're thinking about this problem space. So the first observation that I'll mention is that there's not going to be a single chip or server type that's going to power the AI workloads of the next decade. This is an interesting trend that's, I think, really been emerging. If I look back a decade, everything ran on sort of a CPU. Most every workload ran on a CPU, maybe one faster, one more core, one slower. But it was pretty standard selection of server types out there. And I think there were a number of reasons for that. One is Moore's law was allowing us to produce better and better general purpose processors, and so having one tool chain made a lot of sense, gave us a lot of leverage. Another reason for it was while it was super complex to build the servers and the infrastructure, and if you needed to support lots of different kinds of servers and lots of different kinds of hardware, that just didn't make a lot of sense when you were trying to focus on your business. But the cloud started to change all that, and we got excited about that about 12 years ago. And the cloud takes away a lot of the problems that come with custom hardware. And so way before AI started growing as quickly as we see today, AWS was innovating to provide more bespoke and custom hardware solutions for all sorts of applications. But then AI came along, and AI is really there's an ecosystem of workload types inside of what we call AI today, and agentic AI is pushing this even faster. And so my excitement is that this now opens up the scale and diversity of workloads that really is going to push innovation all the way down. Of course, we all are here today because of the GPU, which is a phenomenal chip that really changed the game when it came to doing this sorts of floating point and matrix operations that underlie most of the AI models that we're building. And it was really a somewhat happy accident that this happened, but it was really a critical part of the origin story of the AI models that we're all so excited about today. But the GPU is a fairly general purpose architecture. It was built, in fact, for what it's named after, graphics. And it may not be the most optimal. In fact, it's not the most optimal hardware architecture to power a lot of the models that we're running today. And we noticed this a better part of a decade ago when we started seeing some of the emerging patterns in AI models. And the interesting thing about the AI models is, yeah, they do a lot of matrix operations and floating point math, but they do them in a fairly predictable way. And so that means that rather than having to have a bunch of cores with a bunch of registers accessing random memory, you can predict the flow of memory and compute through a chip. And the type of chip that is most optimal for that kind of workload is actually something called a systolic array. And so we started building our Trainium processor, which we originally called Inferentia, but grew into a larger variant, which we now call Trainium, better part of a decade ago, based on a systolic array architecture. And that architecture has allowed us to achieve efficiency by removing a lot of the flexibility that we don't need for these workloads, while still preserving a lot of important flexibility to allow it to run a broad range of different types of ML models. It's not an ASIC customized for one application. It's an AI accelerator that's been built specifically to optimally run the biggest and broadest range of AI models. But even though we think Trainium is the optimal architecture for AI model building and inference today, it's very unlikely that one chip is going to be the solution as we look at how AI workloads are evolving. And that's exciting. We think there's another decade or two of novel innovations that we can put into Trainium, pushing the limits of what's possible there. But we also think we're going to invest in other chips, and others are going to invest in other chips. And I think that's going to make the hardware ecosystem that we're all building to much more interesting and exciting. One quick example I'll give there that most folks in the room might be familiar with is the inference pipeline. When you look at the transformer models that we're running today, the autoregressive transformer models that are the vast majority of the models that are underpinning the agents that we all are talking about, there's two workloads underneath that inference. There's the prefill or encoding workflow, which is extremely compute intensive. And then there's the autoregressive token generation workload, which actually happens to be extremely memory bandwidth because each subsequent token requires us to access every model weight. And so the profile of those two workloads is radically different if you look at it at a hardware level. And Trainium is actually designed very well to run both of these workloads today. That efficient memory flow that I talked about benefits the decode workload, and the large floating point performance is great for the prefill part of the workload. But there are other patterns emerging that might allow for optimization of one or both of those parts of the pipeline. And the one that's getting the most attention right now is the token generation portion with so-called SRAM chips, or chips where we put a lot more memory on the compute chip at the expense of compute capacity itself. It's all a trade-off. And the result is that you can run the token generation part of the workload significantly faster. But that comes with trade-offs and constraints. If you want to run something that needs a lot more compute, well, you traded those transistors for memory. And if you need a lot more memory, you probably can't fit it on the chip in the first place. And if you're running agentic AI, you probably need really, really long context windows. And it's hard to move that context in and out of an SRAM chip, much more expensive than it would be with something like Trainium. And so I happen to believe that SRAM and memory-intensive chips are going to play an important part of our inference systems, but in the context of many other chips, not as a replacement for the chips that we're using today. All right, I'll move to the second observation I want to talk about, which is that models and chips must be designed in tandem. And this may seem fairly obvious, but it's not exactly how we've been doing it up till now, at least not broadly. And the fundamental observation I'll give you here is that when you're building an AI model, you're making a multi-year investment in building to a certain model architecture, and that could be an extremely expensive investment, hundreds of millions of dollars, and I suspect in the not too distant future, some of the model families will be investing billions of dollars in order to progress. And so when you're making that sort of long-term investment, you want to be efficient at every step of the process. And a chip investment is very similar. The lead time on building a new chip and bringing it to scale in a data center, it could easily be 2 to 3 years with the complexity of leading AI processors. And so now if you have two long arc investment pieces like that fundamentally need to be co-developed, it would be a mistake to sort of develop models in isolation of understanding what's going to happen in hardware a year from now, or to be building hardware for 2 years from now without understanding the needs of models. And so bringing together the design of the model and the system around the model and the hardware chip is fundamental. One quick way to think about this is just think about the capabilities that you put on the chip. Again, I said it could be 2 to 3 years from when you're designing a chip to when you're putting it into production. And one of the places that you look, of course, for new ideas for what you might want to put in your chip, in your hardware, is in academia. And here I have, I believe, I can't see it on my screen, but I think there's a bunch of very important Berkeley papers in here. And there's a lot of good ideas in these papers. But not every one of them is going to be something that makes its way to production, not because it was a good idea, but because when you make design choices, you can only make so many design choices. And so the art of building great hardware is understanding which of the great ideas ultimately need to be put into hardware, so that by the time the hardware is in market, the science and the technology is ready to take advantage of that chip. And that's exactly what we've been doing with Trainium. You can see on the board some of the features that we've been adding to the latest generation. And these were very much inspired by work in academia, but also research in our customers and our internal teams. And so we're really excited. About 6 months ago, we brought our internal foundational model closer together with our chip development. That's a big part of my purview now, and it's going to help us continue to bring some of the most capable hardware innovations and models to our customers. The third and final observation I'll make for the morning is that, and I've already kind of touched on this, AI infrastructure is not a model problem, it's not a chip problem, it's a systems problem. And this makes it like one of the most interesting problems, I think, that you get to work on as an engineer or as a scientist, because literally these systems are so interconnected that if you want to get performance, and we can define performance as better accuracy, we can define performance as lower latency, we can define performance as better throughput and cost, but any of those betters requires a complete understanding of every level of the stack. And when done well, it brings in almost every part of computer science engineering, which just makes it an incredibly fun place to play as an engineer and as a builder. So ultimately, and I would say, we've had a real focus because we believe that in order to get the best performance out of our system, we've had a real focus with our chips programs at Amazon, making sure that we give customers the deepest access to our hardware. And that's because when you're trying to optimize performance, you don't want abstractions between you and other things. As a computer scientist and spending many years in software engineering, I have an instinctual desire to put a layer of indirection between things to scale. And that is usually the right way to build software, particularly if you've got a large organization like Amazon. But it's not the right way to build an AI system if you want to achieve absolute best performance. There you need to lay hands on the whole stack. You need to understand the network. You need to understand the chip. You need to get to the hardware instruction level capabilities of your chip and your network. And so that's exactly what we've done with Trainium. We've exposed our complete instruction set. There's many students here at Berkeley that have helped us push the limits of what's possible there. We've also open sourced our tool chain so that folks can understand how our compiler is working and how other parts of our software stack work. And of course, we've integrated with things like PyTorch and VLLM, which are key parts of the building ecosystem. And so, I'll end by just saying, the fact that we have this amazing opportunity, but the world is full of constraints, capacity constraints, performance constraints, power constraints, that's what makes this whole thing so interesting. And that's why I'm excited to be involved in technology and AI at this very moment. I hope it's why this audience is also excited. The future is bright, and we need to build it together. And I'll echo something that was said already earlier this morning, which is events like this that bring together experts and visionaries from all parts of the stack are critical to unlocking the potentials that come from understanding the whole system. And so there's never been a better time to be at an event like this, and I hope that this weekend is fun for everybody. So I'll leave you with my thought that I started with, which is this is the very beginning of this journey, and what lies ahead is going to be far more exciting than what we've seen to this date. And so, be motivated, be excited, and build. Thank you.